I used to work for 6 years in the embedded area, so mostly for automotive industry. Recently switched to another area, but the 6 years, they were very educational for me. And since a while, I was thinking about actually making a presentation with an overview of the embedded systems problematics, including the various architectural specifics, and review the applicability. Review the applicability of the C++ language for the embedded development. Also, with some examples, of course, how the C++ can be applied, how it can be used, and of course, where are the limitations for C++ for this particular area. So, why I wanted to present this. So, I think that there are like two worlds. The one is there is a software engineering world, yeah, and the people working there, they are very interested in the language features, in some best practices, in the tools, frameworks. I would even say that there is some form of a cult of the code quality in the good meaning of this world. At the same time, there is a fascinating world of embedded systems. There is a great experience accumulated for hardware, software interaction, different specifics of optimization. A lot to learn there and a lot to do there. And the one can really see how hardware works and work on a very low level, understanding many fundamental things. At the same time, software is quite often a secondary thing there. Unfortunately, not always. There is an overlap here, but I would like to maybe encourage some exchange between these worlds, between people working, because there's a lot to do in embedded and a lot to learn there, but also a lot to contribute there as well. So this is some motivation behind this talk. So let's dive into the topic. So if we are talking about embedded systems, so what is an embedded system? So the embedded system is a specialized computer system that is designed to be a part of another system. So normally it performs some functions that are service functions and that support the functionality of the primary system. And we see a lot of examples nowadays of the embedded system. So if we look at the modern vehicle, the modern car, there we will see a network of these so-called ECUs, electronic control units. They can be of different complexity, but there are many of them. They are interconnected, they communicate with each other. If we look at the consumer devices, there we can also see like a large group of devices that quite often is really grouped by the same name, but a very different device, like for example, smart devices. And now it's everywhere, the smart devices. And we can have some remote control smart lock, for example, or some smart watering device for a plant, or a smartphone with the functionality of the mobile computer. Those are the different devices, yeah, completely different devices, but also, and just to get the common properties and to describe the common properties of different different types of embedded systems, I would like to highlight some groups that, in the purpose of this particular presentation, I just would like to highlight the following four primary groups. So the one is the group of the embedded systems with so-called limited resources. So there is no such a metric. What does it mean, the limited resources? But it should be expected that as the system is specialized and it's designed for a particular purpose, and at the same time, the production costs should be reduced. Quite often, the size should be reduced, and energy efficiency, so consumption should be reduced. And that means that there will be not that, so the resources that will be available, the hardware resources. By resources, I mean the operational memory, RAM, some flash space for storage of the executable, or the CPU itself, so kind of the microcontroller that processes the that runs the functionality. So they can be, so these resources, they will be just designed to be just enough. So that means that the design should consider that. Software should be aware of this. So another group of the embedded systems is the real-time systems. So here it is that this is also a large group. There are subgroups of this of the real-time systems, but it's important that we can say about this that those are the systems that have some extra requirements, that they should be capable of performing their functions with respect to some deadlines. So that means that, for example, if there is some incoming signal, it should process the signal and respond to it, not exceeding some particular time interval. What is important here is that to reason about the correctness of the design, we should be able to, of the real-time systems, we should be able to analyze the worst-case execution scenario. That we should understand what will be the longest path if the signal comes, so how long it will take in the worst case to process some particular signal. And to be able to do this, the system should have the property should have the property of deterministic behavior. So it means that it should be in some predictable state, and the execution path from the state should be also predictable. We will return to this a bit later. And there is another group, some critical systems. Critical, I mean, this is also a large group, but we can talk about safety critical, mission critical systems. The specifics there is that it's not only that in development of the systems, followed some guidelines. In the architecture, so this criticality is reflected in architecture, it's also reflected in the standards that are applied for writing the code. It brings some limitations, some requirements, and this should be also considered. There is a fourth group, everything else that is not in these three primary groups. We have large variety of other embedded systems, and quite often we see that there are embedded systems that are providing some human-machine interaction, for example, like the different ATMs or entertainment systems within the cars. Those are the systems that are quite often based on the embedded versions of general purpose operating systems. And development for them, it's not that much different, in fact. So, of course, there is specifics, but it's not that much different than development for just the desktop or server versions of these general purpose operating systems. From the process point of view, what is so specific about the development of the embedded systems? So we are mostly talking about the cross-tooling there. So because we develop and build the software and deploy it on the different platforms. So this, of course, increases some deployment time, so feedback from the system that it works also is increased. It's not always quite convenient, actually, to do this, just from the developer perspective. And this is something that would be nice to actually minimize, that to make it possible to work mostly on the, for example, to write the code mostly on the developer's machine and be able to test it, for example, and then only to deploy it and to verify it on the target when at least like the logical correctness can be verified before that. And so the also a very important feature is that the diagnostics and debugging capabilities, they can be limited. They can be artificially limited due to the security concerns. They can be also limited due to the platform of technology limitations. And also the system where the software is deployed, it can be actually just physically hardly accessible. Doesn't necessarily mean that it's in the space, but it can be deployed somewhere very far distant, some telecommunication equipment, for example. And it is important that actually to consider that. So it's not always accessible. And to also important characteristics that quite often the development of the hardware happens in parallel with development of software. Not maybe completely in parallel, but the improvements can happen. Some bug fix on the hardware level can also happen. So it is possible that there are hardware bugs are present. So this is something that never happens, but can happen. Yeah, so there is a possibility that hardware is not working properly. And the same thing happens with compilers. So especially if the proprietary things, proprietary compiler, proprietary tooling is used, this can be that there can be some bugs that can stay there for quite a while before they are fixed. So this is also this is a problem. And as a kind of consequences of this, I would highlight that it is I would even say crucial to minimize the defects and to actually maximize the quality of the code before any deployment of on the target architecture. So maximum, the best practices could be, of course, applied. All different approaches that are designed to improve the code quality should be used as well. Of course, test-driven design, different forms of continuous integration, and of course, as I already said, it would be really convenient and also improve the developer's productivity if code can be written and tested on the platform. For this, it is important that the code is designed in some portable way so that it can be deployed on the hardware, but also can be at least in some testing environment, at least like in a unit test environment, can be executed on the developer's platform. So so for especially, it also reflects my opinion. So this will help a lot. So now just can be very naive, but for those who are interested in the topic but might be never touched it before, so let me just give a very short introduction in some trivial hardware platform, just to understand what we will be talking further, and also to maybe agree on some terminology that I will be using. So here we see a very simplified version of the hardware that can be used for developing some hardware software platform. So this is a core, some microcontroller. It has the pins. The pins, they are connected to the board. These are the normally called these general purpose input-output. So these are the input-output lines that can be used to communicate with some peripheral devices. So they are controlled using the so-called memory-mapped input-output. That means that the particular line state, actually percents of the current on this line, can be controlled using some bit or set of bits in some particular memory cell. These memory cells, they are called special functions register. This is not the CPU register, but it's just the terminology that is used. This is just a memory address, and this memory address is known as a hardware specification. Also about the terminology, so the group of these lines, it can be also called port, but it's not the port-bound input-output as in, for example, x86. So this is just the name that is used. So the group of lines can be grouped in the port. So at the same time, on the microcontroller, they can be also already integrated submodules that are already implementing some functionality. Like, for example, here there is an integrated universal asynchronous receiver transmitter. So it also has the lines. They are not general purpose. They are just for transmitting and receiving the data using the UART protocol. And it is in a similar way controlled via the memory mapped input-output. So some particular addresses are responsible for activating this module transmission, to activating the transmission, receiving the data, sending the data. On this trivial hardware platform, some trivial software can be executed. So here it's some really simple software architecture. that can effectively, that can be deployed on some hardware like that. So we have here the signals that are coming from the connected devices that are connected via these pins, those peripheral devices. They are coming and they are transmitted to the application logic via the mechanism of these MMIO registers and interrupt service routine. So the interrupt is the mechanism that allows us to actually specify some routine that will be executed when the state of the line is changed. So this is similar to the more complex systems. The logic can be based on just on a simple loop, and it will be processing the data. So either some global objects that will be modified by interrupt service routines, or just polling this MMIO register to understand in what state it is. What is interesting here is that due to its simplicity, it actually has quite a deterministic behavior, because it's either somewhere in the loop or in interrupt handler. So we can reason about what are the paths of execution in case of some incoming signals when they are coming. So how long it can take, for example, at maximum with some rate of the incoming signals. But this is really simple. So here is just only some sensor can be implemented like that. If we will be considering more complex architecture of the system that already has some functionality for some interaction with other components, some connectivity, some diagnostics, then our simple architecture will scale to something like this. We will need to have some scheduler, of course, priority-based and preemptive. It will control the set of predefined tasks. So the set of tasks that will be in the system, it will be defined on the design stage, in fact. So we will know what are the tasks that are available, and there will be no like dynamic parallelism. So everything, all the parallel tasks that will be working there, they will have assigned priority, and they will be always known at the ready design time. So the interaction between the tasks will be most likely executed via the queues. So the queues, they will be synchronized, but the tasks, they will be working only with the data that coming from these queues, or with some resources that they will not share. So there will be some tasks that will be responsible for interacting with some particular peripheral devices. This is to avoid any conflict for the resources that can lead to the indeterministic behavior. So these queues, they can be different depending. So, for example, for more performance critical tasks that are reacting on the information coming from the sensor, they can be very highly optimized. For less or for more application-specific tasks, like for example here in diagnostics, it can be more reusable code, so more developer-friendly, I would say. So but what is important is that there is no other communication between the tasks, only via this queues. So, and what is interesting here is if we also analyze the application for the high-performance applications that are not designed for embedded platforms, we will see some similarities here. So we will have also task-based parallelism. We will have quite often this reactive architecture with asynchronous interaction between different tasks. Of course, it will be important to minimize the resource contention and the sharing of resources, and of course also there will be a need to optimize memory usage, but this we will cover a bit later. And yeah, so there is a huge overlap in between the embedded and non-embedded real-time and high-performance systems. This is also reflected in the fact that in C++ standardization committee, that the groups that are working on the game development, also high frequency trading, and also on the embedded, they kind of joined the effort. Yeah, so now they are covering the efforts for standardization of the performance specific things together. So it's covered by one study group. Yeah. So now a bit about the programming language requirements. So here it's, I think, quite, if we analyze what is required, what is the specifics of the language that we would like to use for development for embedded, yeah, we would definitely like to have the minimum overhead, for sure. As we discussed before, it's nice because we are talking about that we are working with a cross development. It's nice when we have the portable, the language that can be used to write the portable code. Some form of test friendliness. I'm hard to say that it is the language feature itself, but I think that some language features they enable the test friendliness, and also always nice when there is an environment for the language where some frameworks are available that can be reused and that we do not need to develop many things from scratch. I personally think that C++ satisfies these requirements, but there can be some limitations of C++ applicability for this kind of the systems. So we need to consider that as we are working for different platforms, yeah. So it might be that particular compilers they are not supporting some of the platforms. This is one of the potential limitations. Standard library cannot be available for some particular platform. So some language, not exactly the language features, but some constructs might be seen critically and risky for particular platforms or particular types of applications. We will cover this. And also, if we are working with some criticality, there can be industrial standards that limit some applicability. So this is also should be considered. So we are talking about the compiler support. There is a very huge progress that was done in some recent years. When I started working in the automotive in 2015, I think there was, even 11 was not yet available. So C++ 11 wasn't yet available. It wasn't. There was no standard for this, and also the compilers they were not supporting this. So there was some experimental support, but certified compilers they were not doing this. Now. Even proprietary things, they are ready at least like on C++ 14. That's already a big progress, really. Of course, if we are working and can use for some of the actual platforms, we can use non-proprietary, open source GCC CLang. They, of course, have much more advanced support of the modern features. But as I said, yeah, so at least C++ 14 that enables us to write quite a modern C++. Of course, yeah. The limitation means that, unfortunately, if we look, yes, in the tables, there are still some features missing. This is even about on the syntax, even on the syntax level. So that's actually all of them. Even the most advanced, they still have some limitations. So about the standard library. So if we can use the open source solutions, and for many platforms we can. Theoretically, for most hardware platforms, we can get the distribution, or we can build the compiler with the support of the so-called hosted version of the standard library. Hosted, in fact, means that it contains features that are dependent on the operating system. This is interesting because it is, so normally the underlying C library, it implements it supports these features. So these dependencies, they are satisfied by this libc, and if they are not satisfied, for example, for GCC, the build system actually creates some stubs, but still built. So the components like file system, they can be available, for example, for some ARM platform, but at the same time, they will be not just working. So the includes, they are there, but the stubs, they are just not unfunctional. So that means that the setup can be, so the setup can contain these includes, and these headers, but the one just cannot use them. But this is an advantage because the hosted, compared to the freestanding that is designed to be non-dependent on operating system, hosted contains at least the STL. So it's the full set of the functions. So the STL for the freestanding library, the STL is not available, mostly due to the exceptions. So because the so the freestanding variant of the library is designed not to be dependent on the exceptions as well. Really hardly usable. No algorithms, no containers. Utility is not there. So this move std forward is not there. So we cannot just use the. There are no facilities to support some fundamental language features as well as move semantics, for example. So this is not nice. And in case of some proprietary, we can have some SDKs that will be. So we can have some SDKs that can have some subset of the standard library. So they will just cherry pick some parts that are working, and of course we'll drop these headers like file system, something that they cannot support. About some particular language constructs. So the two primary constructs that are considered to introduce the risks, they are heap allocation and exceptions. And depending on what type of the system we are designing and implementing, we need to consider that. For the heap allocation, in case of limited resources, it might be that there is not enough space just to maintain the heap, just to bring in the overhead for the heap organization. At the same time, fragmentation can also consume some part of the memory that is not just available for us. For the real-time systems, the heap allocation can introduce some. So due to fragmentation that is unpredictable, and some access synchronization, as the heap is a kind of global resource, it can increase, so it can just lead to indeterministic behavior that we want to avoid, to reason about the possibility to process our data in the restricted time slot. In case of exceptions, for the limited resources, it might happen that the increase of the code size, of the executable size, can be too critical. For the real-time, the analysis complexity and potential loss of determinism as well. So this vision changes a bit. So I think that. So the exceptions, they are not seen as critical as they were seen before, but this is reflected in the industrial standards that we can review here. So those are the standards, some standards for some safety mission critical software. We can see here this Joint Strike Force Vehicle C++ is quite famous one because Björn Strausstrup was participating in development of this one. It is from 2005. Two other standards are automotive standards, so the MISRA C++ or AutoZAR C++ 14. So for the heap allocation, actually they limit it to a very large extent. So in GSF, the heap allocation is allowed only for the initialization of the system. In Misra C++, it's just completely prohibited. In AutoSAR C++ 14, there are limits. So it is allowed, but there are limitations that it should be deterministic. So it's in fact just doesn't work with the global heap. And with the exceptions, it is visible here that is due to the limitations of the tooling that were available by the 2005, they decided that, not to use exceptions. But other two standards, they actually see that less critical. So they recommend to use, so they require to use their exceptions in the way how the core guidelines recommended actually for handling the exceptional situations, like not as a kind of error code or something, as a return code, but just really handle this. In this, under these conditions, they are actually allowed to use it. So we discussed the in general the C++ applicability. So what are the limitations? Now I would like to go a bit to some examples of the applicability. So in the parts, so to look at the parts where the C++ I think can be very beneficial. And one of the examples is the development of device drivers. So this is not a new topic, but I think it's quite worth mentioning it here as well. And another one, so I would like to go through some development of this event queue. We will not be, of course, developing some production code, but it's a good example, it's a good case to discuss how the containers can be used and how the containers can be used under the conditions of the limitations of the heap memory allocation, for example. So, and we will focus on it a bit later. So, about the device drivers. So, as we saw, so we have this memory mapped input-output, and we have this memory mapped register. And the fundamental thing there is that we need to communicate with the devices using this MMIO, using this MMIO approach. Yeah. So here is some code that is taken from the SDK for some quite minimalist hardware platform that facilitates some input-output operations for the different registers. We can see that there are some addresses that are specified, and there is some calculation of these addresses that is happening. Then there are operations that are essentially the bit operations to make the mask that corresponds to some particular bit. The bit controls the line, yes, so as we discussed before. And then just the write operation is modification of the address that was calculated. So it is modification of the data referenced by the address that is calculated here. So this implementation introduces some issues because, first of all, this API that we just discussed, it is dependent on the hardware platform for which it is designed. So it cannot be separately tested. So we cannot make sure that the code itself works. The code that uses this code also cannot be tested independently because it is, again, dependent on the specific platform. At the same time, we see that there's a work with addresses, there are some bit operations, and it would be nice to actually have some compile time checks that at least like when we make a mask and we try to put it into some register that is 4 bits long, that this mask at least like 4 bits long as well and doesn't anyhow like exceed this limit. So I would just like to discuss how we can use C++ to maybe kind of improve the situation a bit. So this is based on some code that I developed as a part of the workshop that I prepared, more like a case, in fact, but to introduce the in general some approach that can be used. So the fundamental thing that we can bring in is that we, of course, can abstract the access to some particular memory addresses. So to abstract and isolate the access to some particular cell in the memory that can be on the target, can be our special functions register that is responsible for some port. So here, for example, we can use template. So in this template, we can specify that we can have some integral type, some fundamental type that reflects the size of the register, that is T, and then we can have some address and maybe base, or yeah. So at least there can be one single constant here that defines, depending on the architecture, where it is located in the memory. And of course, the access to that would be quite simple. Yeah, so we just need to reinterpret the data that is located entered by this address to have a type that we specified here. So after we have this form of the abstraction, we can have some architecture-specific alias that will limit a bit the, that will be, sorry. So for concrete architecture, that will use the terminology of this architecture, and also will be using, so the constants, some constants that are specific for this architecture and specified in the documentation. And using this approach, we can specify actually just some type that would be responsible, will be isolating the access to some concrete register. Then later, we can specify what bits, some mask that we want to modify, and just call the set function that will effectively access the memory cell and set it, and modify the bit in this cell. This approach, when everything is done in the compile time, when we specify the mask, the location, of course, enables us to actually make the compile time checks for the correctness of the mask that we are using in respect to the registers and their sizes in for which we are building this wrapper. Here I'm using enable if tag dispatching can be used for C++14. No, sorry. So enable if underscore T is the so enable underscore T, so it's enable if can be used. Yeah. So if we do not have this. So depending on the standard that we have, and also some optimization can be done. Again, because everything is in a compile time, we can check if, for example, the mask that we want to modify, and we fully control the register so that the register is of the size that is really like the size of a byte or multiple of a byte, so that we can override it if we want to set it without necessity to read it, then modify and write it back. So this can be also done on the compile time. So here is the const expression is used, if const expression is used, but can be substituted by tag dispatching. So the advantage of this approach is that for the testing purpose, we can have our abstraction for address access and for address calculation can be substituted to provide the address of some variable with the static duration. If we do this, we can use some mock address. We can have some static variable. We can have the our mock. Our mocking facilities that are injected in our write object for the testing purposes to provide the access to our static object. And in this way, we can just test the correctness of the modification of the registers that we want to have. So we are able to test our code. It's not only just, and we can verify that that the framework that we developed, it is actually functional. So having this access to particular registers isolated, these modules can be used to develop more complex software, and also can be this software that depends on these abstractions can be developed in the test-driven development, using test-driven development approach. When we are developing the, for example, device driver, it would be really nice if it will not be dependent, of course, on the real implementation that just modifies some hardware, some real registers for some particular platform, but instead can have the dependencies on some abstractions that can be substituted by mock objects. Here I just wanted to make a remark that for the embedded, it is quite important that we do not introduce some extra overhead. And when we are designing some code and considering the dependency injection, it's important to take into consideration that our two primary approaches that we have, the runtime polymorphism and compile time polymorphism, they have their specifics. Especially for the runtime polymorphism, we are limiting ourselves in the way that we are we introduce the virtual call there. So, and we are becoming dependent on the compiler if it can be virtualized. Otherwise, we will have some indirection and overhead of the virtual call. This can be critical for the performance part of the code. So because this extra indirection, extra code that should be executed to implement this indirection is actually an overhead. And not to be dependent on the compiler ability to remove that and to have the portable, that is not available for every compiler that can be used for embedded development. Alternative approach with the kind of compile time dependency injection can be used. So here, there will be no virtual call. There will be possible to enforce the inlining, or the compiler will actually make inlining for us. That will be a good candidate for inlining. And we don't need to build the hierarchies where we don't where there are no like real relations just for the purpose of the substitution by the mock. As an example, it can be something like this. So we have some driver, for example, our UART control. And it can be designed in a way that it is dependent on some particular bit that activates the transmission. So we can mock this bit. Here is an example on the, for the GTest, based on the GTest framework, GTest GMock framework. So we can just integrate, so we can inject this type instead of the original type if we make the code generic, that is, and without the concrete type being without the UART control being dependent on the concrete type here. So and then we can inject it, set up the expectations, and here again the C++17 feature is used that we do not provide the template parameters here because they are deducted from the constructor from the types of the parameters of the constructor. But what is important here is that this TX control bit, it is injected in a way that the UART control is just dependent on some generalized on the template parameter that we can specify here. So this allows us to inject any type that basically behaves like this bit, and in our case that will be a mock that will have this set of functions. So the driver that we implement allows us, without introducing the overhead, to test the correctness of our logic. So this is crucial. I personally find this crucial for implementing the reliable and maintainable software, and embedded especially. So some intermediate summary for this development. So the compile time polymorphism with this compile time dependency injection that we reviewed, it really allows us to develop this testable components without introducing the extra overhead. abstractions for this memory mapped input-output, they are not anyhow novel. Yeah, so there are many. There are several frameworks. For example, Quasir from Odin-Holmes that uses a quite interesting metaprogramming approach. This is the one that it's actually worth of visiting, but none of these frameworks they became de facto standard, unfortunately. The language is going forward. Might be this topic can be revisited, and actually even more kind of usable things will appear. So, quite an interesting topic, I would say. So, I think that's all for this device driver development, and I'm actually standing here blocking the vision. Yeah, so I'm sorry. The next thing that I also wanted to review is the application of C++ and the usage of the different containers. For the as I mentioned before, so we can look at the development of the message queue here, event queue, as a case for this particular purpose. As we mentioned before, there are limitations regarding the memory allocations. So the heap allocation is syncritical in the embedded environment. So what are the alternatives? What can be done to actually avoid this? And there are several. So it might be that we can use only objects with automatic and static storage duration. Also, we can use for the containers, we can have some containers that have some embedded storage. So also, without the dynamic allocation, so with some predefined size. We can implement the custom allocation that we also that will allocate some data that within the container, within the buffers that will have also static or automatic storage duration. The pool allocation, similar approach, yes. And we can also use some intrusive containers that allow us to connect the items that have the automatic or storage duration into the container. So those are the techniques that should be considered, and they are actually interesting not only from the embedded point of view, but in general from the performance point of view as well. So. As we discussed this, especially if we are starting to work in this area, it's quite important. So, do we need to implement everything that we discussed before? I mean, these containers, these different non-heap data structures by ourselves, or we can actually reuse something that is already available in the frameworks that are available in the large environment of the C++ language. In fact, to a very large extent, many things that we would like to have, they're already available. Of course, when we are talking about some frameworks for C++, first of all, we probably would look at Boost. There are several containers or several facilities that can help us to avoid heap allocation. We will review them a bit later. There is another one. There is a framework called Electronic Arts STL. So this one is designed for game development, in fact. But as we discussed before, so as the problematic overlaps, and the heap allocation is also critical in the game development as well, there are facilities that are available, and they can be reused for embedded applications as well. The STL by design uses the heap allocation, but the allocator abstraction allows us to avoid it to some extent, but with some limitations as well. So these frameworks, the Boost and ASTL, I do not provide the licensing information here, but in general, they are available for the commercial development as well. So, and STL, yes, so it's a part of the standard library, part of hosted part. Let's just go through some examples and see how we can write more than C++ kind of event queue. And with the help of avoiding the heap allocation, to some extent avoiding exceptions if we would like to do that, and also at the same time writing more or less modern code. So first of all, let's have a look at the event type. Yeah, so we will need, this is an example. Yeah, so this isn't by no means any kind of production, just to demonstrate some things that we can use. And this is worth of mentioning that they exist. And just by example, let's kind of look at them. So the event type. Event type, it would have the timestamp. Yeah, so probably because we will need to specify when it should be handled. This is quite simple. Timestamp can be of some integral type. But for the, for example, if we want to make some kind of a reusable queue, we can, it would be nice to provide some abstractions in form of the closure. So what code should be executed there? Here we are entering the interesting problem because, for example, the standard function cannot be used here because even the variant of the standard function with the custom allocator was deprecated. But we need to use the dynamic allocation to store the capture list. So here, the facilities from the ASTL actually are very helpful because they have a lot of classes, yeah, a lot of that have the similar functionality to the standard classes, but providing this so-called fixed storage. So here we on the compile time should specify what is the maximum size of this capture list, and just this would allow us to avoid the allocation at the same time providing the closure. In fact, it is not that much of the limitation because normally we actually know what are the capture lists, so we can reason about what is the maximum size of this. This is a trade-off. Yes, it's not that dynamic, so there can be some overhead due to some larger blocks that are predefined, but at the same time, it definitely avoids, it allows us to avoid the heap allocation for this. And the same thing with the string, by the way. So we have some optimizations, yes, but at the same time, the string, of course, allocates memory. So to avoid this allocation, we can use the fixed string as well. So we need to specify the maximum size. But it's all about, unfortunately, in embedded, this is quite typical. Yeah, so we definitely have always this trade-off. So we need to provide some static sizes that might be exceeding, so introduce some overhead, but this is the way how we avoid dynamic allocation. Yeah, so this was highlighted here, sorry. So the our event type, we need to store in some container. If we would like to go and to use the standard vector for this, so we will definitely need to provide some custom allocator for this. So the custom allocator that will just have some embedded storage, like for example, statically allocated at some point, and it will need to provide the storage to the vector using the standard allocator interface. What is important here is that, unfortunately, the standard allocator and the standard container, they do not support the reallocation or extension of the storage. So that means that it will be important that this whole space that can be available should be returned once, and the vector should explicitly ask for that. So here, the reserve should be called with the size that the standard allocator, that our custom allocator would be able to provide. And we will need to control the size here externally, or rely on the exception, yes. So looks So this solves the problem, but it looks a bit like a workaround, but can be done like this. So highlighted this as well. Sorry, just now a bit about the container compatibility. So what is quite good about the boost about the standard? Yeah, so that the containers are in general compatible, and if we would like to use the standard containers together with the boost containers, we actually can do this. And this example shows that, for example, we can use, for example, an alternative to the approach that we described before, that is called a static vector from the boost. This is the vector that already implements what we achieved in the previous example. So it just has the internal storage of the predefined size, and all allocation will be happening. So it's not like array. So there is a dynamic. It doesn't initialize the items within. So it just has the dynamic size of the dynamic number of items, but the storage has the predefined size. Effectively, not using the dynamic allocation. And for the purpose of our queue, we would event queue. We would like to use the standard priority queue that uses as the storage backend our static vector. So here we are using the standard one because it's compatible. At the same time, we can also use the boost priority queue that has some extra functionality. But anyway, so this is just an example that we can use the facilities from from different frameworks, from the boost and from the standard framework. And in our case, this priority queue is responsible for sorting. We can specify the so it is not so it needs to have a backend where it really stores the data, but all the sorting algorithms implemented as in this adapter. Our static vector works for this. Unfortunately, with the queue, so as the objects that becoming larger, so these different the storage, so the storing the objects in the vector, they can become a bit of the expensive just because the different shifts and the swaps that are implemented as a part of the priority queue algorithms, of the heap algorithms that they use for this priority queue, they can introduce some overhead. So might be we can go to some containers that are in fact block containers, but also have a fixed size. So this again, the ESTL is very helpful here, because we can see here that there is a for example fixed set that allows us to predefine the maximum size of the set, and it implements the tree structure internally, but at the same time using the static storage. This allows us to, so apart from this fixed set, there are also fixed map, fixed hash map. So there's quite a rich functionality available there. This is the maximum capacity that we need to specify, and also there is a possibility that probably not very relevant for embedded environment to actually specify a backup allocator. So this is a form of optimization for non-embedded, probably where the heap allocation is still possible, so that up to some number of elements it's statically allocated, then the backup goes into the dynamic allocation. This is possible. But we just specify that we do not use it by providing this false parameter, so false value as a non-time to play parameter here. And yeah, so we need to control the size as well as the previous examples if we want to avoid the exception handling. Another approach that can be used, yeah, so we can have pool allocation. Here it's combined example of the pool allocation and with the intrusive containers. So if we have the items and we have the items, they are all of the same size, we can actually benefit from the pool allocation because this can be using, so we can have we can use the approach where the data, so that we can so the intrusive data structures, they are built using the following approach: that all the data that is responsible for the maintaining of the data structure, it's already embedded in the object that is stored within the data structure, within the container. This allows us to use the approach when we specify the where we can store the data and allocate the data once, and as the object size are always the same because they have this static we have so the object, everything that object contains, it already also has the static size. So that means that one single allocation is possible to allocate everything that object actually owns. From that point of view, we can use some pool allocation, and here this can be facilitated via the boost pool, or actually using the very simple implementation of this simple segregated storage that is a part of the boost framework that allows for the constant time to allocate data block of the fixed size. This will allow us to allocate the memory for an object and actually having everything already prepared and just add it into the container without any extra allocation. So this is an optimization not only relevant for embedded, but also for just real-time applications, just for desktop or server applications. We can also implement some custom allocations for our event type. Here, it can be a bit tricky because, as we discussed, we would like to still avoid the access to some global pools, to some global resources. Here, the problem is that we, as the operator new, operator delete, they are static, in fact. So then all the objects of this class, they will be accessing some global structure to implement this. As we have the static structure for the most of these embedded real-time applications, and we know what tasks we will have, so we can introduce the, so we can generalize this code and introduce the template parameter that will be responsible for the ID of the task where this event will be used. So this will allow to have this different instantiations for different tasks, and the allocations of the different objects will be happening from the different instances of the pool. So effectively effectively avoiding the competition for the resources. So, and for this, as I said, so the prerequisite for this is that we know all the tasks that will be existing in our system, so we can actually allocate the different pools for different tasks. But this is how it is typically happening in the real-time embedded applications. So the event allocator here will be also dependent on this ID. So this will be another instantiation. So it's another object, and that's how it goes. Another interest. Yeah, apologize. Yeah. So there are types in the standard library that are also guaranteed to not perform the dynamic allocation. They can be also leveraged to access to implement some logic that quite often requires the, for example, the dynamic polymorphism. So here, for example, as an example, here there is an example with the standard variant that can be used to implement some form of the runtime polymorphism. Let's assume that we have two different types of the transport. So the one is SPI and of the UART. This is just low-level protocols, and we have a factory method that can return either SPI or UART transports. It returns the variant that can store either SPI or UART structures, and they have these methods sent. So here we actually using the generic lambda and the visitor, we can go into some duck typing mode here, and this will, without any runtime polymorphism, will actually call the send function of the real object that is stored in this transport. So this would allow us to to have the behavior that is dependent on the runtime value that was returned from this function. So this is some form of runtime polymorphism. Quite often, we will need to have a dynamic memory allocation to allocate the exact. So if we are using dynamic polymorphism, quite often we will need to allocate dynamic memory for the type that should be returned, or at least we can also avoid the just the virtual function call. But this is just an example that there are several classes within the standard library that by no means should be neglected. So that's because they have some guarantees that are quite important and quite useful in the embedded environment. So the variant, it is available in the standard library. There are also alternatives in the boost. There is also alternative in non-STD. So there are several frameworks where it can be done and where it can be taken if the standard library is not available. As we discussed before, so if we would like to avoid the exception, so it is not seen that critical, but if we want to, so we need to kind of maintain some proper error handling as well. Here we can at least maybe go into the direction of the some usage of the optional, for example, more, because this is also, there is no dynamic allocation for this. So when we need to return either result or some Boolean, if it was retrieved or not, for example, here we can use just the optional values. This helps a lot, and also quite a modern way. Or we can use variant with some error code, or we can use some specialized implementation that are also available. So, for example, as a open source frameworks, for example, non-STD expected to error handle, or actually boost outcome, that are also quite useful and even like more flexible. So those are the techniques that can be used to avoid some standard problems. And so those are the things I think were probably the last things that I wanted to look at this during this talk, and just wanted to come to the conclusion. So from my impression, yeah, so the best practices for development of the software, yeah, so this writing code is quite important in the embedded, in the development for embedded systems. And I think that these practices, they are quite well known for C++ community, so the C++ community can actually contribute a lot to the embedded development. So this is quite obvious for me. This is my impression. C++ language itself, I think it has the features that enable development of the portable and testable code. So this, like encapsulation, different types of polymorphism that allow us to provide this unit tests and dependency injection, even without overhead, as we reviewed that. The third-party frameworks can enable developers in the embedded areas to write the code, quite a modern code, avoiding still the limitations that are imposed by the realities of the task that they're working for or by the standards. And of course, there is a huge overlap in between between the high-performance non-embedded and high-performance embedded applications. So, and I think that it's of course shows that the knowledge exchange is beneficial. At the same time, it also shows that the engineers who are interested in embedded, they can bring a lot from the other areas, and at the same time also learn a lot. Yeah, that's probably all for this talk. I thank you very much for your attention, and maybe now we can switch to questions. Thank you.